Today we're going to talk about the Doppler effect, and it's something that maybe you haven't learned at school, but you're definitely familiar with. And that's, for example, you see when an ambulance drives past you, and then it sounds very high pitched, and then after it passes you, then it suddenly sounds very low pitched. And the reason this happens is that the ambulance is driving forward and it's chasing its own waves, the waves that it's giving off. And this means that the waves in front of the ambulance get compressed, so they sound higher pitched, and the waves at the back of the ambulance get dilated, and then they, of course, sound lower pitch. As easy as that. So what we're going to do is to deduce mathematically how to calculate the shift in frequencies for someone who's standing here and someone who's standing here, and then also for someone who's running towards the car and away from the car. And you'll see it's pretty straightforward. Once you've done one, you've done them all, and then we will end up with a very big formula, and well, it's something that you can either remember or you can just use your data booklet, but it's not extremely complex. What's complex is just keeping track of who's moving where, what's constant, what's not constant, and all that stuff. So let's get started. All right, so we've got two things. We've got a source that's moving with a certain speed Vs, because it's the source. And then we've got an observer that's still, and everything that relates to the observer is going to have an O in it, so that we know it's the observer. And this thing is emitting some waves of a wavelength lambda, which of course are going to be a little squeezed in here because this is moving towards them. Okay? Now what I'm going to do is to calculate the wavelength that this guy measures. And the wavelength that this guy measures I'm going to call lambda observer, as opposed to lambda source, which is the wavelength that this guy would measure. Okay? Now the lambda of the source is just c, the speed of sound, times the period. Right? Now after one period though, this guy has moved a distance d, and its distance will be equal to its speed times that same period. Therefore, the wavelength that this guy measured is just this minus this, because yeah, this has moved a distance ct, but then by the time the next wavefront is emitted, this guy has already moved a distance vst. So the difference between these two will be the wavelength that this guy observes. Therefore, this wavelength is equal to ct minus vst and is equal to t c minus velocity of the source. Now what happens is that we don't really want things in terms of the wavelength, because sometimes we'll have this guy still and this guy's moving this way, and then the wavelength doesn't change, but what does change is the frequency. So we want everything in terms of the frequency, because that's what always changes. So I'm going to re-express this in terms of the frequency, and I'm going to also re-express this in terms of the frequency, and then we'll be all happy. Now, first thing for this, well, the period is the period for this guy, the period between two waves. Therefore, this is just 1 over the frequency of the source. Good. Now for this one, all we need to do, now he measures a speed of sound that's the same as this guy has. So for this guy, we have that the wavelength measured by the observer is c over the frequency measured by the observer. So now all we need to do is plug this in here, and then substitute this by 1 over fs for the source, and then we're done. So let's do this. We got that c over the frequency measured by the observer equals 1 over the frequency measured by the source times c minus the speed of the source. Great. And now what we need to do is to turn this around. So let me zoom out a little bit. And now I'm just going to turn this around. So I'm going to flip this 2 and flip this 2. So I've got that the frequency measured by the observer over c equals the frequency measured by the source over c minus velocity of the source. And then from here, it's pretty straightforward. I just need to put the c over here. So I get that the frequency of the observer is the frequency of the source times c over c minus velocity of the source. And now I don't really like the way this is put because I have two c's here. So I'm just going to divide this by c and divide this by c to get the final formula. So I've got that the frequency as measured by the observer is going to be the frequency of the source divided by 1 minus velocity of the source over c. And remember, in this case, c is the speed of sound, not the speed of light. Cool. So we've got our first Doppler effect formula for a source that's approaching the observer. Now I want you to stop for a second and think, what if this guy was moving this way? How would you modify this formula so that things worked out well? Give yourself 5 seconds to think about it. Okay, hopefully you listen to me. And of course, if this thing is moving this way, all we need to do is reverse this sign of the velocity, right? So minus plus, minus is for when it's approaching, plus is for when it's going away. So that's the first part and the hardest part. Now we just need to keep doing this again, this time with a stationary source and an observer that's moving. So in this case we've got a stationary source, so I'm going to draw a person because people move less, and let's just say he's got a megaphone, and we've got an observer that's running towards it. And we want to know what the shift in frequency is. Now in this case, both guys will measure exactly the same wavelength because, you know, there's this length and these waves don't compress. They're still the same wave. So when this guy goes through, it's still the same wavelength. What changes though is the frequency, because this guy goes through the wave faster than he would be if he was just standing there. Therefore, he will see the front waves hit it more often, and therefore the frequency will increase. So we're going to do the same thing we did before, and we're going to find a formula that's very, very similar, and then we're going to do the same thing that we did with this guy moving backwards. Right, so let's get started. Now the first thing is acknowledging that that the wavelength measured by the observer is equal to the wavelength measured by the source. And this is going to help us out later. And now we need to think, okay, so what's the frequency that the source measures? Well, that's really easy. We just use the wave equation, which remember is just the velocity equation with different letters, right? So, okay, let's do that. Now, what I'm going to use is distance equals speed times time. Okay, so let's see that the lambda measured by the source, that's the distance, will be equal to the speed that it measures, it's just the speed of sound c, times the time, which is the period as measured by the source. And then I'm going to change this around, and I'm going to substitute the period by the frequency. Just remember that frequency is 1 divided by period. And we're done. Now we need to do exactly the same thing for this guy over here. Good. Now you'll see that this is very, very easy because, well, the wavelength is the same, and all that changes is the speed. Now in this case, the speed of sound that this guy measures is higher because it's not only c, it's c plus v, because this guy is approaching the waves. So all I need to do is replace this by c plus vs. Sorry, vo, which is the velocity of the observer. So let's do that. Then I'll say that the lambda measured by the observer, which is the same one as the lambda measured by the source, so I'm just going to use the same letter. So this also has to equal c plus vo divided by the frequency that the observer measures. And now all I need to do, because these two things are equal, all I need to do is to equal them, and I can figure out this in terms of this. So let's do this again. We have that c over the frequency of the source equals c plus vo over the frequency of the observer, and then all we need to do is rearrange this. So we got that the frequency of the observer that goes over here is equal to the frequency of the source times C plus VO over C. And again, we don't like this so much. We're going to rearrange this so that it looks a little bit like the one that we figured out before. So we're going to have frequency of the observer is 1 plus V over C times the frequency of the source. And that seems to make sense, right? Because this frequency will be higher than the one that this one measures, and that's what we expect because this one's moving towards the wave. Now again, give yourself 2 seconds to figure out what happens to this equation when the observer is moving away from the guy who's emitting the sound, so the source. Now hopefully you did what I asked you and figured out that all we need to do is to add a minus sign. So now we have 2 formulas. We have one for a moving observer, we have one for a moving source, and what we're going to do is put them together and combine them. And then we're going to have the formula for the Doppler effect, which can have moving sources, observers, whatever you want, that works. Cool, so we've got 2 formulas. The first for the moving source. Now the one that's on top is for the source that's moving forward. The one that's on the bottom, the plus, is when it's moving backwards. For the observer, this one's for when it's moving forward. This one's when it's moving backwards. And if you don't remember which one is which, all you need to do is use your common sense. So what do I expect? Do I expect an increase in frequency or a decrease? And then you look at the equations and see which sign will give you the increase or the decrease in frequency that you expect. So all we need to do now is put them together. Now, this is extremely easy. All we need to do is substitute this by all this. So, I mean, you can check that this works if you want, but it's really just common sense. The total formula that incorporates both things at the same time will just be the frequency of the source, and then if the observer is moving, then 1 plus minus VO over C. And if the source is moving, then 1 minus plus Vs over C. And you can very easily check that when the observer or the source are still, then this formula reduces to either of those. So this gives us the right result for any situation. So we're done. That's all we need to know. The formula for the Doppler effect. Now, the rest of the job is yours. And to leave you, I'll leave you with a photo of Sheldon dressed as the Doppler effect. As you can see, the frequency is higher here and lower in there. I'll see you tomorrow.